Hi, all. Good evening. My name is Kishore. I'm from Team 7. So we are here to present about spine disease classification using deep learning. So for today, agenda we'll be talking about data pre-processing step, data preparation, data analytics in this project, proposed and developed machine learning models, and the system design we are planning for this project. So data collection pre-processing involves a series of steps. So the whole project kinds of goes through the data, and the project goes through these following steps. So first we learned about different kinds of diseases that affect the swine. The most commonly the respiratory system as well as the skin. So these are two different kinds of organs. The symptoms will be very different. So we have different kinds of data we'll be working with. One is audio and one is image. So the first step starts from data collection. So we collect the steps involves of collecting data from various sources for the different kinds of data types. So next data pre-processing, followed by feature extraction, followed by data preparation, followed by data splitting, which will be for the models. And after this step, basically the data will be ready for the modeling. So coming to the data requirements, so this project has some tasks to be checked off to be completed project. So this task has a specific requirements from the data. So this table basically describes the task which has to be completed and the data characteristic that it has to process. So first starting with cuff sound analysis. To do the cuff sound analysis, we need audio recordings of swine curves to detect the detection of swine behavior anomalies. We should have audio recordings of swine normal behavior. Then we can distinguish between normal behavior and anomaly behavior. So then we have to do classification of swine curves. So for that, we need labeled data set of cup audio recordings. So then followed by skin disease classification. For this, we need high resolution skin images. So for identification of common symptoms through image analysis, we need diverse data set of skin lesion associated with swine diseases. So for the first step, as we spoke earlier, it's data collection for the images. So the first step is to learn about different kinds of different kinds of diseases that affect the swine respiratory as well as the swine skin. So we learned about these kind of diseases through some veterinary websites. So some of these websites have a database which have all these kinds of images and audio data. So Iowa State University Veterinary Department, we downloaded the images from Iowa State University Department, Center for Food Security and Public Health, Cornell Veterinary Medicine, and we topped up these database with our own Google search. So we downloaded .jpg format files for total of 13 different skin diseases. So ranging from American swine fever, African swine fever to swine vascular disease. So for audio data collection, we got our hands on a specific audio data set which has a segmented cup sounds. So cup sounds of three different kinds of diseases: pneumonia, porcupine reproductive and respiratory syndrome, and African swine fever. So it has a like 5 to 10 seconds audio clip sounds of pickups that the pickups that are going through these kind of diseases, these three diseases. So the next step in this project is data pre-processing. So we implemented for data pre for the audio involves implementing augmentation and synthesis to the or existing audio files and following up on the previous questions by professor in the previous presentation. So we came up with evolution of these synthesis and augmentation model. So as professor asked, like how do we know that the augmented or synthesis and synthesis models are good to use for the classification purpose, good to be like as similar to the original audios. So we did implemented objective evaluation and subjective evaluation. So in objective evaluation, we implemented a metric called signal to noise ratio. So where it compares amount of signal present in audio file compared to the noise in the audio file. So anything about 13 decibels is good for classification. Anything above more than 20 is very good for classification technique, classification process or classification tasks. So we gone with basic level, which is 10 and above. So we are saving the files, we are saving the augmented files and synthesis files which are having the signal to noise ratio of more than 10 decibels. As you can see in the snapshot here, if any file that is having less than 10 decibels, we are not saving it. So we are saving, you can see here, you can see, as you can see in the snapshot, there are 3 files. So out of 3 files, only one is saved because the signal to noise ratio is more than 10 decibels. So after that, we did subject evaluation where we picked randomly some audio files which have been saved and compare and listen to them carefully if they sound similar to the cuff sounds. So the data augmentation segment synthesis techniques includes pitch shifting, stretching, accelerating, adding noise. So coming to the data pre-processing for the image data set. So instead of manually labeling all the images, we automated the process by labeling the image when it reads a file, when it reads for the file from the folder. The folder name will be the label for the images. So that's the first step. As you can see in the code, even the code dissipates whatever I'm saying about like the labeling part and all. So then we researched the image to 224 because we went for these numbers because we tried with different kinds of numbers and we got very good, like good accuracy for these numbers when compared to the remaining remaining sizes we tried for. It's a trail and error method. So then we decode the JPG format to tensor format to obtain the pixel values, color channels, which will be further needed for the feature extraction and for the model to learn better. So then we did then we did image augmentation, we did random flip, rotation, and contrast to increase the diversity of the data set. So the pre-processing of the image dataset also typically involves normalization and transforming the data which the model is expecting to. And as you can see in the code, so that's what the basically the code is doing. So it's reading the image and pre-processing the image, like cropping the image. So the next step is data preparation, which will be talked by Ramya.
So the data flow diagram represents the flow of the data through various stages in the system to detect the diseases, swine diseases using both audio and image data sets. The flow starts with the user inputting the data, either image or audio data, into the system. The data is stored in the AWS, which is followed by pre-processing stage. In the pre-processing stage, the data is cleaned or resizing of the images or removing the noises in the audio data, and whatever the required cleaning is done in the pre-processing stages, followed by the data preparation, the extraction of features of audio and image data features are extracted in the preparation stage, and the splitting of the data into training, testing, and validation is done in the data preparation. So then the data, according to the input data, the data is flown into the model, either a audio disease classification or image disease classification, and the output is extracted in the last stage. Moving on to the next slide. The feature extraction for audio data sets, the features are extracted using MFCCs, which is mel frequency cepstral coefficients. These are these are the compact features that extract the required characteristics of an audio signals. The extraction of MFCCs involves various stages like pre-emphasis, frame blocking, fast Fourier transformations, followed by mel filtering and log filtering. So the resulting coefficients, which represents the compact features of the audio signals that are used for the model building. Uh, the feature extraction of the image data is, we used a pre-trained CNN model to be specific. Inception V3 is used to extract the features of the image dataset for the from the pre-processed images. Moving on to the next step, in the data preparation, the next step is splitting of the data into training, testing, and validation data sets. For the audio data, we used a ratio of 60-20-20 for training, testing, and validation. So there is a snippet of the number of data samples that are divided for training, validation, and testing. And here is a distribution of each class for training, testing, and validation are represented in the pie chart. Moving on to the next step, the image, we use the same training, testing, validation split ratio for the image data set as well. in as like the audio data set, which is 60, 20, and 20. And the each class distribution of for the training, testing, and validation is represented in the below bar graphs. Moving on to the next step. Here are the analytical results of the data. So in the pre-processing stage, the audio data samples consist of around 1080 data samples with a storage size of 119 MB. For the image data set that we collected before the pre-processing stage, we have around 259 samples, which is around 1.5 MB data. In the data transformation stage, for the audio data, MFCs that we extracted consist of 1080 rows with 2 columns. And for the features of image dataset that we collected consist of 259 rows with 2028 columns. And after the training, testing, and validation split of the audio data, we have around 648 training sets, 216 samples of testing, and 216 of validation data samples of audio data. And for the image data split, we have around 115 of training, 52 samples of testing, and 52 samples of validation data for image samples. Moving on to the next slide. Here are the visual representation of mathematical analysis that we conducted for audio data samples. We calculated the mean, median, and mean minimum size and maximum size of audio duration of the samples. And we also represented each disease samples in the bar chart. We we also represented the audio duration of the data samples of each disease in the following frequency chart. Moving on to the data analytic results of image data set. Here are the visual representation of all the data samples in a bar chart. And we also calculated the mean, median, and the distributions of each disease in the mathematical analysis. And we also visually represented the mean, standard deviation, and maximum of each feature for each data set in the as a graph. Moving on to the next. The proposed models will be explained by Rajiv.
Thank you, Ramya. Coming to the proposed models, initially we experimented with machine learning models such as SVC and random forest. Following the guidance of our professor, we transitioned to move to more advanced models, including DenseNet, ResNet, RNN, LSTM, and MobileNet, considered to be among the best in the field. So at first, DenseNet, densely connected CNN architecture where each layer is connected to every other layer in a feed-forward fashion. This connectivity patterns enhances feature propagation, resulting in solid feature learning. Here in this picture, we are passing input as audios, and followingly dense block and transition layer, and we are predicting output as pneumonia. Next slide, please. Yeah. This is the architecture of DenseNet. Here, DenseNet employs the ReLU activation function to introduce nonlinearity, while dropout is incorporated to prevent overfitting. The output shape is set to 3, reflecting the total number of classes in the classification task. Coming to the ResNet, a deep neural network architecture known for effectively handling deep networks. Residual blocks help to solve the vanishing gradient problems. Here, DenseNet plays a ResNet audio input undergoes a sequential processing pipeline. Next slide, please. In this architecture, audio input undergoes a sequential processing pipeline through components such as the basic block, ResNet block, SE block, RESENE block, and feature recalibration. This structure enables the model to effectively capture and refine audio features at various levels, facilitating a comprehensive understanding of the input data. Ultimately, the output is generated based on the prescribed flow depicted in the diagram. And coming to the RNN, it is specialized in processing the sequence for tasks such as speech recognition or language modeling. And it is capable of maintaining information in memory over time to capture temporal dependencies. Effective for analyzing time series data or sequential data like audio signals, where past information influences the current state. Coming to next slide, please. And this is the architecture of recurrent neural network. Coming to the LSTM, here we are using LSTM for image classification. It's an advanced RNN architecture capable of learning long-term dependencies in sequential data, ideal for time series analysis, image classification, natural language processing, and speech recognition tasks. And it effectively handles sequence of image features like pixel values, capturing temporal dynamics critical for understanding video and image data. Here in this diagram, we are passing pig images as input, following inception v3 and extracting the features and the architecture, and we are predicting output as PRRS. Next slide, please. And the last model is MobileNet, a class of efficient models for mobile and embedded vision applications, optimized for speed and size while maintaining accuracy, utilizing depth-wise separable convolution. In this context, MobileNet can effectively process visual data with lower computational resources, making it suitable for real-time application on mobile devices such as facial recognition and object detection. Next slide, please. Coming to the results, in the evaluation results, 3 models, DenseNet, RNN, and ResNet, were tested on audio data. For DenseNet, the accuracy was 80 with precision at 53, recall at 72, and F1 score at 61. Coming to the RNN, performed slightly better with an accuracy of 81. And ResNet achieved an accuracy of 80 with precision at 84. Additionally, 2 models, LSTM and MobileNet, were assessed on image data. LSTM achieved an accuracy of 36, which was lower, and MobileNet performed better with an accuracy of 46. These results provide insights into the model performance across different data types, with RNN showing the highest accuracy among the audio models and MobileNet performing LSTM in image data classification. Next part is system design. Shrutik will take care of designing the system.
Thank you, Rajiv. Coming to the system design, this appraisal is a significant issue in the pig farming sector, which is highly permanent and influential. The swine industry is crucial for the meat, but timely disease detection is challenging part. Here, the farmers plays a key role as an actor in caring for pigs. Yet tracking all the pigs in the large facilities can be difficult. So late examination may lead to the severe issues. So to address this, early disease detection using pig vocalizations and skin images is very essential. So we have collected both kinds of data set, like audio and images, which will be stored in the system boundary. Coming to the system boundary, sorry, the data sets will be stored in the cloud, and later these data will be translated into the pre-processing process, wherein which can be converted from video to audio and all the raw images into a particular image data set. And later part, this will be into transfer to the data segmentation part. After data segmentation, machine learning models will be executed. Before that, you can see the data, both the kinds of data are training to predict the output with the high accuracy, like forecasting type of illnesses, including the user interfaces. As you've seen in this UI part, we can upload an image and we can predict what type of diseases is the pig is having, in which it can forecast its diseases. And moreover, data analytics necessities the collection and pre-processing analysis are the insubstantial data volumes are crucial for supporting the system's essentials operation. Where this data can be predict what kind of disease the pig is having, in which if it's error, it can be easily detect it's a false disease. Well, coming to the systems architecture, the user interface has coming to the system architecture, in which the front end and both the back end. Where coming to the GUI part, you can see the front end part. What actually back end happens is we collected both the kind of data, which is audio and images, in which the data deep learning models are executed. Later, the training and testing validation parts are segregated, in which we can easily predict what the actual diseases. The actual diseases will be displayed in the front end part. Well, next slide, please. Coming to the future scope, well, uh, coming to the future scope, the boost current deep learning structures and methods to enhance the model efficiency on visual and auditory datasets, can modify the model's hyperparameters and regularization strategies, and also can create the realistic audio samples according to the GANs for the data enhancement by integrating this generative adversarial networks, which is GAN. Well, again, coming to the leveraging transferring learning, in future to apply a knowledge from large scale of datasets to particular picture and particular audio tasks, can use to transfer learning techniques and pre-trained models, and optimize the pre-trained models using the target datasets to make use of the obtained features and boost training efficiencies. Investigating the assembles approaches to merge predictions from many models and taking advantage of each architecture's advantages for enhanced performance across the range of datasets. Well, thank you, and the demo will be performed by my fellow friend Ramya.
Sorry for that. I'm Kishore. So I'll be going ahead with the demo. So first, let's go through the data pre-processing for the audit data set, which we did for this project. So this, whatever the code you're going to be looking at, that's a demo code which will be running for this project. So as I told, so this is the data pre-processing for the audio files. So these are the libraries and packages that we particularly needed for the data pre-processing. So as we spoke earlier in the presentation, we need a SNR metric to evaluate the augmented and synthesis data audio files. So this is the function that basically calculates the SNR ratio. So we have given the input directory and output directory. So this particular loop executes the whole code, runs the major part of the code about the data pre-processing. So it reads the files from the folder input folder, and we automated the code so that it automatically creates a folder in the output path with the same name and the same label names. The label for the each audio file is automated, and it will be taken from this folder name. So as you can see here, so we just make sure the length of audio file has been similar, all the audio files are same, so that we can do the data augmentation and data synthesis. So we're doing the data processing with the first package, which is first library, which is PyDub. So in PyDub, you're using faster, slower, reverse the audio, and audio shifted the pitch. And similarly, we did some more audio processing with Librosa library with straight shift and adding noise to it. So as we told earlier, we automated the process of saving the files to a specific path. So this function which will define the output path as well as the name of the file. So if you have a file that in which the audio is shifted, so the output file name will be audio shifted. So if it's stretched, it will say audio stretched. So that will be easy for the identification. And why we're going with saving, because instead of just like reading the files, process it and go ahead with the model developing, in case if any error happens, we lose all the process data and it takes so much time to again process all this data. So it's for the sake of saving memory, we are saving sake of running time, we are saving these files in a separate folder, so that will be easy to access this process folders, so that we don't need to run the pre-processing again and again for each and every time if we do a trial and error. So here comes the main part. As we told, is use the above function SNR ratio. It will save the files only if the SNR ratio is more than 10 decibels. As we spoke earlier, above 10 is good for the classification task. So here, this function, this loop will make sure we'll save the files only if the SNR ratio is more than 10. So as you can see here, samples here. So the SNR ratio is below 0. So augmented is not saved. It's about 22, it's saved. So this is the one of the processing for the audio. And coming to the pre-processing for the image. Oh, sorry. So once the each and audio is processed, so this audio processed has been, you can see here, PNU is the name. So pneumonia. So pneumonia faster, pneumonia noisy, pneumonia pitch shifted, pneumonia reversed, as I told you earlier. So the file name will be whatever augmentation it went through. And it was given for a class ID. So we have three classes, pneumonia, PRS, and African swine fever. So it has a class ID. As I show you, this is the class distribution for the different kinds of diseases we have, different kinds of files we have. So this is just exploratory data analysis where we where we visualize the input data in different formats using this one using Librosa, and this part is using PyDub. So coming to here, next step, which is just as I told you, it's exploratory data analysis. We visualize the pneumonia samples of different samples. And data pre-processing for the audio data, we do feature extraction. We extract the features using MFCCs. So these are the MFCCs for the complete audio files. So later on, we divided them into, as you can see here, class and the feature. So later on, we divided them into test, train, and validation. But before going at that, so the audio files, all like the features all are not same length for the safe of for the model to run at good rate as well as to get good accuracy. We padded these files. So this step shows the sequence of padding for the all the features. So as I told earlier, after the data conversion, after the data splitting, here is the training and test set, 824 and 286 in the training and test set. So later on, we implemented few models, and one of them is DenseNet. As you can see, this is the structural layout for the DenseNet. It has dense layers. It has activation function to implement non-linearity into the model so that the model learns about non-linear functions in the model. So without this, the model will not be able to learn any non-linear features in the model in the input data. Also, to make sure that there's been no overfitting as well as there is no overfit underfitting, we added dropout layers so that the model doesn't learn more than what we need, like to get a good accuracy in the sense. So, and you can see at the end, the output shape is 3 because then the output class is only 3. Like we have PRRS, African swine fever, and pneumonia. So there are 3 classes. So we have output shape is 3. So this is this basic of training the model for running for 10 epochs. We got good accuracy, but not compared to other models. Other models perform well. This one got an accuracy of around 72%. So it's fine, but not that good. As Razi is speaking, these are the earlier implemented models, which are SVC and random forest classifier. And coming to the image dataset, I also had gone through some pre-processing steps, then data preparation, data transformation, which is feature extraction. Then we implemented a series of different machine learning models, which is LSTM and MobileNet. So let us go through the pre-processing steps of image as well as LSTM implementation. So these are all the packages that are needed as well as libraries that are needed for the feature extraction, the pre-processing, and other steps of it. So similar to the audio processing, again, instead of doing manual labeling, we just automated the labeling. So whenever an image is read from a file, the folder name will be the label for the image. So this is what it's doing. And also we are cropping the image. You can see we can keep the target size here. So this loop basically iterates it, reads the image, crops it, and it will convert to numpy array of all the list of arrays. So you can see here how many number of images in each category. And this is just a visual representation of how many images are, how many number of images in each category. And this is the visualization of images after they've been read and cropped. You can see here. So this image is read from a swinepox folder. So the label is swinepox, and you can see the list of different images with the labels. And so as Ramya spoke about it, so we do use a Inception v3 to extract the features. This part of code extract the features, whichever read the image, right? Those read images go through this Inception v3 to extract features. So here is the feature shape which we like extracted, and here is the feature values that have been extracted. So each feature is kind of a pixel value So this CNN which we implement LSTM is RNN. So the next we follow mobile net V2 will learn these features. And again, we split the data to 60, 20, 20 because that's a standard way of doing it. And also we following the research paper. So these fall, they do 60, 20, 20, and we took that as an inspiration. We're working on it. So here is a defining the LSTM model. LSTM model defined here, the LSTM model, which will be basically classify these features. So then we compile the model and we train the model. We train for 10 epochs. As you can see, the train and validation loss, there's a very big gap. That's not a good sign. It says the model is overfitting. So we have to change the parameters. We have to increase the number of layers in the LSTM. Maybe we have to try working on it, but that's for the next step. As of now, we got something to work on. So for the future step, as we did for DenseNet, we can try to increase the number of layers in between, to add dropout layer, to add some more features like some more softmax layers, or some kind of regulation technique, some kind of, we used optimizer as Adam, we can try with something else. So there's a lot of things to try on, but this is what as of now it's happening. So for the test accuracy, we got around 36% is not so good, but mobile net we got around like 48%. Even it's working far better than LSTM, but 48% is not a good accuracy when compared with what already existing models. So this is the demo of all the models and the code we implemented. Thank you.